In this lecture, we're going to talk about crystal field theory, specifically how it's based on Coulombs Law. To discuss crystal field theory, we'll need to talk about the shape of d orbitals, because crystal field theory is a specific theory to talk about bonding for transition metal complexes. And all of our transition metals have their valence electrons are in d orbitals. And finally, we'll talk about the crystal field splitting for octahedral, square planar, and tetrahedral coordination spheres. All right, in the last lecture, I mentioned that coordination complexes often have really beautiful colors. And so we want to talk about crystal field theory because it's a theory that helps us to describe both the color and magnetism of transition metal complexes. Okay, so as we mentioned in the last lecture, crystal field theory is based on this concept that the metal-ligand bond is purely electrostatic. So we can think of everything like point charges, that the electrons on the metal are point negative charges and the electrons on our ligands are point negative charges or negative point charges. To be able to use Coulombs law says that your potential energy increases if you have two negative charges that are coming close together. It's going to destabilize, or that potential energy is going to get higher. So for us to talk about crystal field theory, we really have to have an understanding of the shape of these 3D orbitals. So let's just go ahead and talk about an example, and then we can get into the shape of these 3D orbitals. Okay, so this complex on the left is hexaaqua chromium 3 plus. And so if we think about chromium, this is going to be an octahedral complex. So I'm going to draw it this way. Okay, for crystal field theory, remember specifically, it is the electrons on the water that are donating to the chromium. So we want to think about this ligand as just a negative point charge. So let's go ahead and redraw this. So again, we're trying to think about this metal ligand bond. Chromium 3 plus has a D count of D3. So typically, we would write out our 5 3D orbitals as degenerate, meaning that they have the same energy. And this is what our electron configuration would look like. However, we need to think about the shape of these 3D orbitals, because some of our 3D orbitals are pointed along our X, Y, and Z axes. So if we're thinking about the same octahedral complex, we're going to define this as the X, Y, and Z axis. What's really important here is that our ligands are pointing along our Cartesian axes. Nature doesn't have a coordinate system, but this is the frame of reference that we're going to be using to talk about this. Our dx squared minus y squared and our dz squared, both of these d orbitals are pointing along the axes and therefore are pointing directly at our ligands in an octahedral coordination sphere. When these ligands start approaching our chromium, so you can imagine, so this is our dx squared minus y squared. So if you think about this also as a negative point charge, as these negative point charges are pointing next to one another, the potential energy is going to increase. What happens is we get this splitting of our d orbitals. D orbitals that are higher in energy are going to be our dx squared minus y squared and our dz squared. The dxy, dxz, and dyz are pointing 45 degrees away from the ligands, so these are going to be lower in energy. And this splitting is called delta octahedral. So it's the difference in energy between T2G and your EG orbitals. And the original energy is called the barycenter. So overall, we have conservation of energy. And you can prove this to yourself. So we have 3 d orbitals that decrease in energy by 2/5 delta octahedral and 2 d orbitals that increase in energy by 3/5 delta octahedral. So if you were to add together all of the changes in energy, you overall would get a net 0 change in energy. We'd have this conservation of energy. So again, this is just another picture showing your 3D orbitals in an octahedral field. So your dx squared minus y squared and your dz squared are pointing, these d orbitals are pointing directly at the ligands. So we have more electron-electron repulsion. And then the dxy, dxz, and dyz are pointing away from the ligands in an octahedral field. So they have a lower potential energy. So in crystal field theory, we can explain color and magnetism in terms of the effect of the ligands on the energies of the d orbitals of the metal ion. So this splitting that we're talking about. So we get this splitting because of the geometry of the ligands. Depending upon the shape that we have, we get different interactions of the d orbitals and the ligands, resulting in different crystal field splittings. So the splitting of your d orbital depends on the relative orientation of the ligands, or we could say the shape or the geometry. So far we've seen it for octahedral, but we'll also show you what tetrahedral and square planar splittings look like. Okay, this is just a figure from your textbook, one more figure from your textbook, again showing that dx squared minus y squared and your dz squared d orbitals are pointing directly at the ligands in an octahedral coordination sphere. So they're higher in energy. We call them the Eg orbitals. And then dxy, dxz, and dyz, we call our T2G orbitals, and they're pointing between the ligands, so they are lower in energy. This is figure 23.18 from the Silverberg textbook, again showing this splitting between our T2G and our Eg orbitals in an octahedral coordination sphere. The other thing that we need to talk about is how big delta octahedral is. So we'll talk about, in the next lecture, we'll talk about factors that affect how big delta octahedral is, but I just want to show you 2 different situations. Both are chromium 2+, but you can see the magnetism is different. Here we have 4 unpaired electrons, and over here we only have 2 unpaired electrons. This case has a larger magnetic moment. This compound has a larger magnetic moment. When your delta octahedral is smaller than your pairing energy, so there's a certain amount of energy required for electrons to pair in an orbital. So there's a pairing energy from electron-electron repulsion. When delta octahedral is smaller than your pairing energy, what happens is your electrons will fill up this higher energy Eg orbital before they pair. So this is what we call a high spin case. Now, if delta octahedral is greater than your pairing energy, these electrons will pair up in the T2G orbital before filling the Eg orbital. And this is what we call the low spin case. And we call these high spin and low spin because high spin compounds will have larger magnetic moments and low spin compounds will have smaller magnetic moments. Okay, so what we're going to be talking about in the next, in a couple lectures is we can use crystal field theory to make predictions about color. So this is really important. So this is an example from your textbook 23.20 of hexa-aqua titanium 3+. We need to talk about this resonance condition. Transition metal complex can absorb light when this condition exists, this resonance condition, when the energy of your photon is equal to your delta octahedral. So when this case occurs, then light is absorbed. And if this light that absorbed is part of the visible spectrum, then we will see color. For this particular titanium complex, we've got this splitting of our Eg and our T2G orbital. This delta octahedral corresponds to an energy of green and yellow light. So green and yellow light will excite an electron from the T2G up to the EG orbital. And the wavelengths that are transmitted are purple, blue, orange, and red. So our green and yellow light is absorbed, and these are the colors that we end up seeing. And so we can make predictions about how big delta octahedral is going to be based on crystal field theory. I just wanted to also talk about what these splitting diagrams look like for other geometries. For the square planar geometry, the ligands are along the x and y Cartesian axes. And remember, your dx squared minus y squared is along your xy axis. And so only your dx squared minus y squared is going to be pointing directly at your ligands. So it's going to be the highest energy. Your dxy will have a little bit of overlap in the xy plane. Remember, your dz squared has that little donut in the middle, so it will also have a little bit of overlap with your ligands along the xy axes, but your lowest energy will be your dxz and your dyz. So this is what a square planar crystal field splitting looks like. And then finally there's tetrahedral. Tetrahedral is a little bit harder to see. So these white balls are showing your octahedral sphere, and they also correspond to your x, y, and z axes. And then these black spheres are your tetrahedral coordination sphere. What you can imagine is it's actually going to be the d orbitals that are rotated 45 degrees off the axes, your xy, xz, and dyz. These will have the most overlap with the ligands. But they don't have as much overlap as, you know, the dx squared minus y squared and dz squared did in the octahedral sphere. Delta tetrahedral is going to be smaller if you compared a comparable octahedral complex. So tetrahedral complexes are typically going to be high spin. So again, for tetrahedral coordination sphere, there's less of an overlap of the d orbitals and the ligands. So your splitting is smaller. Your dx squared minus y squared and dz squared are lower in energy, and dxy, dxz, and dyz are higher in energy. So it's sort of like a flip of octahedral and tetrahedral. The splitting sort of swaps, and you end up getting, you still get conservation of energy, but now dxy, dxz, and dyz are raised 2/5 delta, and dx squared minus y squared and dz squared are lowered 3/5 delta. Okay, so let's just look at an example. This is manganese 2+. If you look at manganese on the periodic table, it's in the 7th column. So 7 minus 2 is 5. So this is going to be a D5 coordination complex. If we were to draw this crystal field splitting diagram, this is going to be octahedral because we have a coordination number of 6. Our EG orbitals will be higher in energy. T2G orbitals will be lower in energy. And we're going to talk about this in the next lecture, but water is not a very strong field ligand. So we'll talk about what that means in the next lecture. So this is most likely going to be a high spin case, which means that our delta octahedral is smaller than our pairing energy. So we're going to fill up our EG orbital before we start pairing in the T2G sublevel. So we can say that this is going to have 5 unpaired electrons. We'll talk about calculating magnetic moment soon, but it's going to have a pretty large magnetic moment. So this is what the splitting pattern would look like for this complex. So in the next lecture, we're going to talk about what factors affect how big delta octahedral is.